Swayam Prabha. Digital India. Educated India.
So we had stopped at the point of three-phase, fully controlled converter. This is where we had stopped. And I think I had drawn the waveform corresponding to alpha equal to 30, alpha equal to 60, alpha equal to 75, and then maybe 90. I said positive and negative sides will be exactly equal to each other, due to which you will have zero voltage. So if you may recall, let me again draw only corresponding to alpha equal to 60, then we will go over to semi-controlled converter. So this is my sinusoid. So this is R or A phase, this is the second phase, and this is going to be the third phase, right? So these are the three phases. So this is the three-phase waveform, and we said that this is going to be alpha equal to 0 degrees. So if we are talking about alpha equal to 60, we said this is where I had to fire 1, and then 2, then 3, then 4, here will be 5. So obviously just the previous one will be 6. 6 would have been fired here for alpha equal to 60. So this is for alpha equal to 60. So this is omega t, this is for alpha equal to 60 degrees. So if this is A, this is B, and this is C, I can again write the interval somewhat like this. So these are the intervals that we are writing here. So this is going to be 5 and 6, this will be 6 and 1, this is 1 and 2, this is 2 and 3, this is 3 and 4, this is 4 and 5. This is how each of those devices pair up with the other one and then conduct. So this we are assuming again continuous conduction, but of course if it is a resistive load, even if it is a resistive load, I would have gotten a waveform. So I am going to look at 6 and 1 conducting, so I have to get VAB. Please note that VAB becomes 0 here, and VAB is clearly positive before that. So I am going to have essentially, this is touching 0, again this will touch 0, this will touch 0, this will touch 0, and so on. Right? This is how the waveform is going to be. If it is a resistive load, I would not have anyway zero current interval persisting for longer, because it might touch 0, even if it is R load, it will touch 0, again it will jump up, the current will jump up. So the 0 interval is not really finite, it is just, it touches 0 and then again jumps up. So this is the way the voltage is going to be. So we said as we increase the firing angle further, I am probably going to see that this gets delayed further, and maybe I will have some negative portion and so on. So this is for alpha greater than 60. Whatever I have drawn for the purple or pink color, whatever I have drawn, that is corresponding to alpha greater than 60. So you are going to have essentially some portion of positive voltage and some portion of negative voltage, both of them, and you might have an average voltage equal to 0. We derived the expression, or I asked you to derive the expression. I don't know whether we derived it in the class, but I said that 3 Vm by pi cos alpha happens to be the VDC average value, where Vm is line voltage peak. Line voltage is line to line voltage. I think this question again should not come up repeatedly. any equipment that is available in the market, if it is a three-phase equipment, the specifications are always given in terms of RMS values of line voltages and RMS values of line currents. So if I say 415 volts, 50 hertz, obviously 415 volts refers to the RMS value of the line to line voltage. Okay, so this question should not come up anymore. Please note it down clearly, underline it in your brain. Okay, please note it down clearly. Any three-phase equipment, the specifications are always like this. And similarly, if I am talking about a motor or a generator, the power rating that is given, 5 kilowatt, 6 kilowatt, whatever, that is the output, not the input, that is the output. Okay, so please remember these things. Being an electrical engineer, you should know at least this much, for sure. Okay, so this is the kind of waveform you are going to get for three-phase fully controlled converter. I think in the exam what I had asked as the question was, this is, you know, connected to the DC link with the battery and a resistance. So a battery is sitting there and maybe that is 380 volts. Maybe this peak is 380 times root 2. I have chosen the numbers in such a way that if it was 415 root 2, I had given a battery of 415 volts. If it is 380 root 2, I had given a battery of 380. It will make my life simpler to solve all of them. That's the reason I had changed the numbers here and there. Firing angles I had changed slightly, of course. So if I have something like this, obviously the resistance will conduct only for this duration. Why would it conduct for any other duration? The devices will be forward biased only when the battery voltage is subdued as compared to the voltage that is coming up across the DC link. Otherwise, the devices are not going to conduct, right? And we are assuming ideal devices, of course. So if at all you have to put down the assumption, you should say ideal devices. That's all. Okay? Anyway, we have done all the analysis using ideal devices. So this will be the voltage across the resistance, and the same will be the current across the resistance as well. So if you want to calculate the current, you could have done it in two ways. Some people have calculated as RMS. People who have done until here, they have calculated whatever is the Vm sin omega t value minus the battery value divided by R, the whole square, and integral of, that is where many people have gone wrong, from what degree to what degree. It will conduct only for 15 degrees. It will not conduct more than that if you actually calculate. So it just calculates, I mean it is starting at 120 and it is going until 135. That is how it will be. So if you have done it and you have calculated the RMS current value, that's fine. Otherwise, if you had calculated VDC average with the complete thing and then minus the battery voltage divided by R as the IDC, I have given still full weightage. No problem. As long as you have calculated IDC like that. And then, of course, whatever is the IDC multiplied by the battery voltage will be roughly the power transferred to the battery. Battery voltage may be slightly fluctuating, but we are ignoring that because we are saying that it's a 380 volts battery or 415 volts battery. We are ignoring whatever is the oscillation in the battery voltage. Right? Okay. So much so for fully controlled converter. I have still not gone for alpha greater than 90. We will take it up after we do the semi-controlled converter for three-phase. So now I am going to venture into three-phase semi-controlled converter. So three-phase semi-controlled converter basically will have 3 SCRs and 3 diodes. So I am going to have 1, 2, 3. I am assuming that the positive devices are SCRs and I am going to assume that the negative devices are diodes. Okay? And then I am going to connect it to the load on the DC side. and I have to give three-phase supply. Some people have drawn the supply like this and that too DC. So here you are going to have the three-phase supply. Right? So this is A, this is B, this is C. Let me call this as T1, T3, T5. This is D6, this is D4, this is D2. Please note that the negative portions go uncontrolled because I have diodes. So the diodes are going to conduct whenever they are forward biased or whenever it is the maximum negative. So wherever I have maximum negative, that particular device will conduct for that 120-degree duration. I will not have any control over the negative side conduction. Whereas positive side conduction, I have control. So let me first of all take the three-phase waveforms. So this is my sinusoid, and this is the second phase, and this is going to be the third phase. Right? So let us say I am looking at alpha equal to 30. So if it is alpha equal to 30, I have to fire T1 here. So I am talking about alpha equal to 30, and this is of course omega t. Right? That is what is alpha equal to 30-degree point. So if this is T1, I am going to have this, this is where T3 will be fired because T2 is a diode here. So I will skip firing that. I cannot fire that because it's a diode. So I'm going to have essentially T3 here and T5 here. This is how different phases are fired. Right? Now, if I say that whatever is the maximum negative, that is what will conduct. Now, during this portion from here until this portion, right? This portion corresponds to, let me write the phases. This is A, this is B, this is C, this is B phase negative. And B phase negative is D6. So here 6 and 1 will conduct. For this duration, 6 and 1 will conduct. Because 1 has been fired here, 6 will conduct for this duration because that is the maximum negative. Whereas here I will have corresponding to 2, the conduction will correspond to 2 because I am going to have maximum negative corresponding to C phase. So this entire portion will correspond to 2. This entire portion will correspond to 2. And this entire portion will correspond to 4 because this is corresponding to the maximum negative, until here. The maximum negative portion until here, not until here, only until here. Maximum negative of A phase takes place until this point, right? So, I am going to have, no matter what, 2 will try to join hands with whatever is the other device that is conducting. So, please note that 6 and 1 conduct only for 30 degrees, not more than 30 degrees. Okay, so this 30-degree conduction portion will correspond to 6 and 1. You understand, from here to here it is 30 degrees. From here until 2 ends up or 3 takes over. So from here until this point where 3 will take over, that will correspond to the conduction of 1 and 2. 1 and 2 are going to conduct for this duration. So let me just try to write the duration. So this is the duration for which 6 and 1 will conduct, and this is the duration for which I am going to have 1 and 2 conducting. So this is going to be the duration for which 3 and 2 and 3 will conduct. Whereas this is the duration for which I am going to have 3 and 4 conducting. Please note, each pair is not conducting for 60-degree duration. This is a much smaller duration. This is only 30 degree, and between these two the duration is 120 degrees. So if 30 degrees is gone here, rest of 90 degrees is coming when I am looking at 1 and 2. So when 1 and 2 are conducting, they are conducting for 90 degrees. Whereas when 6 and 1 are conducting, they are conducting only for 30 degrees. Right? Let me again redraw the waveform here so that we will be able to draw completely the line currents and so on and so forth. So this is my one of the phases, and this is the second phase, and this is going to be the third phase. Right? So I am talking about, this is omega t, alpha equal to 30 degrees. So we said that here is where we fire T1, this is T3, this is T5. So we said that for this entire duration, let me probably draw the duration itself. From here to here, I am going to have, this is corresponding to A phase, B phase and C phase. So this is going to be device number 2. This is corresponding to device number, this is A, so 4, and this is going to be 6. Right? So I can right away say which device is joining hands with which other one. So I should be able to say that from here to here, I am having 1 and 6, and from here to here, I am having 1 and 2. So this is 1 and 6, and this is 1 and 2. So earlier also we talked about this. A phase zero crossing is here, A phase peak is here, right? And this point is 30 degrees ahead of A phase peak, which means that is same as AB peak, because VA and VAB are shifted from each other by 30 degrees and VAB is leading. Please recall the phasor diagram. If this is A, this is B, this is C, I am going to have AB, so this is minus B, so I will have VAB somewhere here. So VAB is 30 degrees ahead of VA when I am assuming that anti-clockwise direction of rotation. Right? So I should say that at this point I should be having VAB peak. So I would have had VAB peak and I must have seen that it is coming down. Right? But after that, VAC would take over, because this is VAB. After this, VAC would take over. 1 and 2, VAC has to come up, right? So when VAC is coming up, again if I look at VAC, so this is minus VC. So if I draw, this is VAC. VAC and VAB are phase shifted from each other by 60 degrees. Right? So if I am having AB peak here, AC peak will happen after 60 degrees. Right? So this is only 30 degrees. So it must have been going up like this, so that the peak happens exactly after 30 degrees from the point where VAB ceases to be the DC link voltage. So I have the peak of VAB here, peak of VAC will be shifted from the original peak of VAB by 60 degrees. That's what I'm trying to get at. So because of which I'm going to have VAC peak coming up after 30 degrees from the beginning of VAC waveform itself. Now from here it is going to come all the way like this, probably. How much it comes down, we'll have to find out, because this is totally 90 degrees. That's what I said. This is 30, this is 90. So this is 30, it should not be in the middle. So it is 30 and then 60 degrees it must have come down. So this is the way I'm going to have VAC. Now again, the next one what I will have is, this is 3 and 2. So that will be VBC. So it will be a repetition again. So I'm going to have something like this. Then I'm going to have until here, right? 3 and 4 for this duration. So I'm going to have again some peaking up here and then it is coming down like this and so on. Right? So this is the kind of waveform I'm going to get for single phase semi-controlled converter when I am looking at alpha equal to 30 degrees. And for this, if I have to write the expression for the voltage, I should say from alpha, right, until what point? That we have to check. Because if I say I am integrating VAB, so I am integrating VAB from alpha until the point VAC is taking over. And VAC is taking over where 2 must have been fired. 2 must have been fired when it is like a diode converter with alpha equal to 0. Right? So 2 will be fired normally at alpha plus 60. Right? 2 will be fired at alpha plus 60. So I should basically say that if I say I am doing from alpha until say it's not alpha plus 60, I should say if this is 0, right, and this is the point which is 60 degrees and this is taking over exactly at 90 degrees. So I have to just integrate between alpha to pi by 2. Alpha plus? No, VAB I can adjust. I can write VAB, right? VAB I can write as Vm sin omega t plus 60. Let me think. No. Please think about it. If I am taking basically VA as, just a second. You are starting with alpha and we are going until 90 and then we are integrating. Let me think. Alpha is actually omega t equal to 30 degree point. So that is the reason why you are saying that I have to make this alpha plus 30. Pi by 2 should be pi by 6. Pi by 3. I agree. Thank you for correcting. So you are getting the hang of it. Good. So in which case I cannot write this as omega t plus 60. It should be omega t plus 30. We are taking reference as VAN. VAN. Everywhere we are taking reference as VAN. So with respect to that we are saying from alpha whatever. We are starting from alpha. So actually my reference is VAC. Then if I am taking VAC as the reference, then this becomes pi by 3, not pi by 2. Agreed. So we are taking here reference to be, so reference is VAC. We have written, yeah. So we are taking basically 60. Oh, I corrected and still wrote 30. Sorry. We are looking at VAC as the reference. So we are firing at alpha with respect to VAC 0 crossing. From alpha, how far it has continued? It has continued until the natural point of conduction of 2. And natural point of conduction of 2 is alpha plus 60, right? But we are taking basically VAC as the reference and we are taking a diode in the negative side. So it should have started conducting exactly at 60 degrees away from the point of alpha equal to 0, which is VAC 0 crossing. So VAC we have taken as the reference. So we are always calculating the alpha from VAC, and from there how far 2 will conduct. I mean 2 will not conduct. How far 2 will not conduct? 2 will not conduct only until 60 degrees point. 60 degree point of VAC. So this is one portion. This is only this portion. We have one more. So here it has to again start from pi by 3. Right? And I have to say clearly T3 is fired at alpha plus 120 degrees. So I don't have to worry about it at all. T3 is fired exactly at alpha equal to 120. Right? And I am going to integrate VAC d omega.